So before we get started, just as an overview, of where we're at in the course, this is the second to last week. So next week will be the final week of class. This week, what you have due, so there's a SmartBook chapter and then quiz 6, which is the last quiz. It's going to cover the last 2 chapters, and then the final chapter that we covered next week will be the final chapter, obviously, and that will also be reflected on the exam 2. So I posted a study guide to Blackboard for exam 2. So exam 2 is going to open up next Thursday, which is I think April 28th. So that's like 9 days from today, and it'll be open for 4 days up through Sunday, May 1st. So you just have to take it during one of those 4 days, and it's going to be it's fairly similar to the last one in terms of its structure and its length. This one does cover like one additional chapter because the first exam covered chapters 1 through 6. This one is covering 7 through 14. So that's 8 total chapters. Here's the study guide that is on Blackboard, which you can download. I think the things to say about it would just be to go through it carefully. You can use it as a guide for studying, and some of the stuff we did go over, it was a few months ago, chapter 7 especially. So it's worth, especially for the chapters that we covered a long time ago, like reviewing it, and you can use this as a guide. I think the slides are the main thing to study, really. So you can use the SmartBook chapters as well in terms of reviewing, but probably your time would be best spent reviewing the slides. And of course, the recordings are also still up, so you can go to those if anything's not clear from the slide. Are there any questions about the exam or anything else in terms of where we're at in the course? And then I guess the final thing to say is that there's the 4th writing assignment is also due. That's 1 week sort of into finals week, Sunday, May 8th. So you have kind of like, I guess, 3 major things left, counting, I guess the quiz is not really a major thing, but so 1 more quiz, an exam, which is just essentially a longer quiz, and then the 4th writing assignment. Any questions?
I had a quick question about the length of the writing assignment. So I think it said 5 to 7 pages. Is that just to make sure that's correct? We can't write any little, it's just that range.
You can't write any little or any, sorry, what, any more?
I'm sorry, I meant to say any less, I'm sorry.
Oh, yeah, you should aim for that amount of length. And so if you're close to that and you feel like you've covered everything, then that's fine probably. But I would just say aim for at least 5 pages of like text, and you can always just sort of go into more detail about the study that you're proposing or the background literature, things like that. And yeah, it shouldn't be longer than 7 pages either. So I think 5 to 7 is a pretty good range. All right. My second screen isn't working today, so my like Zoom stuff, which I don't think you guys can see, is blocking the title of these slides. But there we go. So this is an overview of chapter 13. As I mentioned at the beginning, it's inferential statistics is the focus, and we'll explain what that is. And so we kind of cover a variety of stuff that would be covered in much more detail. Like if you went to grad school for psychology and took a stats class, this is sort of stuff that you would cover really like it would take a semester in a grad level course to cover all this stuff in sufficient detail. So kind of the challenge of today is that we're trying to sort of do an overview of a bunch of stuff that, like I said, sort of there's a lot more to it than just what we're going to cover today. So parts of today might be a little confusing just because sort of the way in which statistical tests are run is somewhat counterintuitive in some cases, but the goal is just to really understand like the main sort of things that we cover, and you don't have to understand like everything about it. You just kind of have to understand like what are these different tests, sort of when we go about testing whether or not a study's results are statistically significant. What does that mean? And I'll do my best to just explain sort of what you need to know essentially, and try to kind of help with things that are a little bit less intuitive. So overall, so inferential statistics is sort of based on this sort of premise that we, as researchers, like we can't really get data about entire populations. So that would require getting, I mean, literally everyone on the planet, or if your population was focused on even just like all UH undergrad students, it would be very difficult to get truly all undergrad UH students to do something. So basically we have to infer the findings that we have, whether or not they actually reflect the population based on a smaller sample of data. So that's what inferential statistics are used to do, basically to see whether or not the findings that we get from a sample are large enough, or there's a big enough difference between two groups, or a big enough correlation that we can infer that there is a true effect in the broader population. So you could think about it kind of like with this graph here, or this image here, where we have, again, think about a population of people. That could be everyone in the US, it could be everyone in the world, it could be everyone in Houston, whatever sort of, wherever you're trying to generalize your results to. And we have to sample from that, meaning that we get a smaller proportion of everyone. And then descriptive statistics is what we covered last week, where you're just kind of trying to describe the results in a study. And you're not necessarily making this sort of inference back to the population. You're just saying, this is how things are in the sample. I will say there's a little bit of overlap between these two. There's a lot of overlap actually, but the main focus of descriptive statistics kind of sticks with the sample. Whereas with inferential statistics, we're testing whether or not we can generalize back to the population, basically. So sort of one general question that inferential statistics ask is that if we were to kind of run a study repeatedly where we keep sampling from the population, and each time we get a different sample, would we find essentially the same results every time, such that the findings from this whatever sample that we have are trustworthy enough that like if we get a different group of people from the population, we'll still find the same things. And yeah, as I mentioned, sort of this differs from the goal of descriptive statistics, where we're really just sticking with kind of the sample. So with inferential statistics, this is where the term statistical significance kind of comes in. And so you've probably heard that term before. Actually, the second writing assignment really kind of covered some stuff related to what we're going to talk about today. Which if you remember the second writing assignment, you had to watch that John Oliver clip, and they talked a little bit about statistical significance, and then you read like a short article about sort of some problems to replicate findings in psychology, which we'll also talk about towards the end of today. But generally speaking, the goal of sort of statistical testing is to help researchers decide if the results that they have from a sample are reliable and generalized to the population. So to test for statistical significance, we have to sort of specify what's called an alpha level, or sometimes this is just called the significance level. And so the alpha level is basically just the probability that we need, that we're claiming that we need to have in order to say that a study's results are statistically significant. So we'll talk more about exactly sort of what this means, but it's basically sort of this sort of cheesy picture here shows on these little things, if you can see it, it says P is less than 0.05, which is typically the P. So the probability is less than 0.05, meaning that like there's like a less than 5% chance that we're going to sort of make a mistake in terms of our statistical inferences. So typically sort of, the alpha level is set at 0.05, meaning that we want to be sort of 95% sure that what we have is a true finding, and we'll kind of allow like a 5% chance that maybe we make a mistake. So you can choose different significance levels. As I mentioned, sort of, 0.05 is typically what we do. But if you wanted to be really sure, you could say like, I want to be 99% sure. So then you would choose a p-value of 0.01. And I think the most important thing, one of the most important things from today anyway, is that statistical significance is really closely related to sample size. So if we have a larger sample, we can be more confident that whatever we sort of find in that sample is actually like reflected in the population, because we have a greater proportion of the population. So overall, we're like, statistical significance tests are sort of set up so that if you have a really small sample, you have to find really extreme results to be confident in them. And that like two groups would really have to differ from each other to say that an experiment worked. Whereas if you have a really big sample, like even sort of small differences between groups are still going to be statistically significant, because we can just be more confident in that whatever we find is sort of a true, real effect. So that's sort of an overview of statistical significance testing. Just to kind of go into a little bit more detail. So everyone should probably be familiar with like a definition of probability. But so with probability, we're talking about the likelihood of something happening. And this is where it gets a little, like I said, sort of counterintuitive, but in statistical inference, so when we're testing for statistical significance, what we kind of are doing ultimately is specifying the probability that an event will occur if there's no difference in the population. So that, to give an example of what that sort of means, so you can think about it like there's some hypothetical, and actually there have been real sort of experiments that psychologists have tried to do, where they see if someone has see if people have extrasensory perception, which stands for, this ESP stands for, which would mean that like you could read someone's mind. If you've ever seen the movie like Matilda, she has ESP. And yeah, there were some studies that kind of looked at like, do people show the ability to like predict something that they truly have no knowledge of at a better than 50% chance, or whatever percent chance it would be, like just from random guessing. So if you have, say your friend claims that they have ESP, and so you want to set up an experiment to test really whether or not they do that. Ultimately, sort of what you would want to see is sort of like, okay, so I'll give you 10 times to test what I'm thinking about. And if you truly do have ESP, like you should get it right at a greater than like whatever, if say there's like 5 things you could possibly be thinking about. So probably 1 out of every 5 times your friend would guess it correctly just out of chance. And so you would need to see that he's guessing what you're thinking about at a significantly sort of greater probability than just 1 in 5. So that's what like this, in terms of statistical inference, what we're specifying is the probability that like an event will occur such that your friend will guess what you're thinking about If there's no difference in the population, which in this case would sort of mean like if he actually didn't have ESP, then what would be the probability that if he guessed like 6 out of 10 times that those results would actually happen? And if it's a really sort of small probability that it would happen, then we can sort of be more confident that he really does have ESP. So partly what with statistical significance testing, we use sampling distributions, which are sort of, they're based on the assumption that the null hypothesis is true, which I'll explain what that means on the next slide. But the null hypothesis is basically just that there's no difference in the population, which would mean that like your friend does not have ESP. So if your friend does not have ESP, and again, there's like a 1 in 5 chance that he could guess what you're thinking about, because there's only a sort of maybe 5 things that you could be thinking about. He'll still guess right like 20% of the time. And so we need to see again that he's doing it at a much better rate than 20% of the time, sort of on average, to really see that he could do it. So to give sort of maybe a more concrete example from like a psychological experiment like we've talked about in this class. So we talked about this sort of data from last week where there's a experiment that looked at basically whether or not children who see like a model of aggression are more likely to be aggressive themselves when they're put in some sort of a room like with a doll, and they could sort of play with the doll in any sort of way they want. And so the question is really just like, does seeing aggression, so this would be the model group who saw an aggressive model, are they more aggressive than people who didn't see an aggressive model before they entered this room? And so this is what you see here are the mean aggression scores in these two groups. You can also see the standard deviation and the variance, which we talked about last week, which indicates sort of how spread out the scores are away from the mean. And then this N is just the number of people in each group. So if you remember from last week, it was just like 10 people in each group. So we have 10 people in each group. Again, this is the experimental group that had the manipulation of watching an aggressive model. This is the control group. And we can see that these mean scores are different from each other. The question is sort of, are they statistically different from each other? And so what we're testing essentially in a statistical significance test is like, can we infer that these mean differences from the sample are large enough such that they would also exist in the broader population? And so it partly has to do with how big these differences are. And it also has to do with the sample size, as I mentioned. So if we actually had like 100 people in each group, these means could be closer to each other, but they would still be statistically significant in terms of their difference. So statistical significance has to do with both sort of the effect size, which is the true difference between groups, and also the sample size. So with inferential statistics, and this is what I sort of mentioned 2 slides ago, is that we're typically sort of actually testing whether or not we can reject the null hypothesis, which is just sort of the idea that there are no differences between groups, or that your friend does not have extrasensory capabilities. So the null hypothesis is just basically sort of predicting that the population means are equal in the case of that experiment. So meaning that like those 2 means that we just saw in the previous slide are not statistically different from each other. They're actually equal in the population, and any sort of observed differences that we have are just due to sort of random error. So the null hypothesis, the word like null means like no, or it didn't sort of like, it didn't work. It was a sort of a null finding. So that would mean basically in the case of that experiment that the independent variable, which was whether or not you saw a model of aggression, had no effect, such that the children in the 2 groups were sort of equal in terms of their aggression levels, even though, again, we did see a difference. But the question is whether or not that difference was large enough that we can be sure that it wasn't due to random error. So we have the null hypothesis, which is always just basically predicting like no effect. And the null hypothesis can sort of be slightly, again, it's always predicting no effect, but it depends on sort of like what the experimental design is, or whether or not you're looking at like a correlational study versus an experiment, like the precise meaning of the null hypothesis. But in like a correlation study, it would just mean that like the correlation is not statistically different from zero, such that like the correlation is zero, or we can't be sure that it's not. So null hypothesis is always saying no effect. And then the research hypothesis is always sort of saying that there is an effect. So that would mean, and it gets a little confusing, I guess, just because there's a lot of sort of negatives here. So like the research hypothesis, which is saying that there is an effect, is actually sort of what it's saying is that the population means are not equal, meaning the two groups, for example, are not equal in that they are different from each other. So that would mean that the independent variable did have an effect such that the children who observed an aggressive model were actually more aggressive than those who did not. So again, that if the population means are not equal, that's sort of what we would want to find if we're trying to see that the study actually worked, so that the differences are big enough that we can reasonably conclude that the population means are also different from each other. So basically, in general, when you hear the term sort of statistically significant, and if the findings were statistically significant, this means that we're confident enough that the population means are not equal, they're different from each other, that we can reject this null hypothesis, which is that the population means are equal. So rejecting the null hypothesis is kind of like a good thing. We're rejecting the fact that there was no difference between groups. And in fact, that means that there were differences between groups. So that's really like this slide is, I know it's a little confusing just because, like I said, there's a lot of sort of like double negatives and sort of things, and rejecting the null hypothesis is kind of a mouthful to say. And if you're interested in grad school in psychology, you'll literally spend like a full year sort of talking about statistical significance testing in like 2 stats classes. And so, like I said, sort of for today, we're just sort of trying to understand the basics. And really, this is one of the most important things, is that because you hear this all the time, that like, oh, the findings were they significant or not? What it's actually just saying is that, yeah, we can reject the null hypothesis, and that means that like we'll have some like reasonable probability that the research hypothesis was supported. So when we have group differences, that is the primary focus. So that's often the case in experiments, where again, we have like a experimental group and a control group, and the experimental group has the sort of manipulation. And then we want to compare whether or not the experimental group is different from the control group. After that experimental manipulation, what we often use is what's called the t-test. So a t-test is a statistic that you would get from like analyzing data, where your primary sort of focus is on seeing whether or not there are mean differences across 2 groups. So whether the mean scores from 2 groups are statistically different from each other. So just sort of like that example that we saw from that aggression experiment, where you saw a mean of like 5.2 in the experimental group and a mean of like 3.1 in the control group. And so a t-test is the formal test that you would use to see whether or not those differences are statistically significant. So the t value is the result of that t-test. So that whatever number you get as your t value is sort of what determines whether or not it's statistically significant. And essentially what the t value, the t statistic reflects is the group difference. So that has to do with the size of like subtracting 3.1 from 5.2. So there was like roughly a group difference of 2. And then we also have to take into account the variability within each group. So that was where like the standard deviation and variance come in. So we need to see that like there's the group difference, that the actual mean difference that we see across the two groups is large enough relative to the variability in each group. So just let me quickly sort of go back to that. So this is, again, this is the mean difference that goes into the numerator of that t-test. So this is just if we subtract this from that, it's 2.1. And then what's in the denominator, the bottom part of the fraction, is either the standard deviation or the variance. So you can see kind of that it's roughly like, it's a little bit different in each group, but it's 1.14 here and 2.1 in the no model group. So again, that's what you're sort of seeing here in general, the mean difference, and then some indicator of like the variance or variability. So there's the specific formula, which you don't really, I'll put a hint here just so you don't have to spend a bunch of time sort of trying to memorize this. This is the sort of full formula if you had equal numbers of participants in each group. As I mentioned, sort of the sample size is also relevant and is reflected in this, such that like the larger samples you have, because this is a square root here, it's going to mean that like this denominator is also larger, so that like the t value that you would need to have to show a group difference would be larger. So that's already sort of more than you need to know, but basically what you need to know from this slide is just that what is the t-test used for? So it's used to examine whether or not mean scores from two groups are statistically different from each other. And up here, sort of what, generally speaking, what it reflects is sort of, there's some sort of group difference in terms of the mean scores, and then we divide that by an indicator of the variance in each group. And that tells us whether or not the results are statistically significant. When you get, so like, this is what's called a sampling distribution, which would be, sampling distributions are typically based on the sort of assumption that the null hypothesis is true, meaning that there is no difference between groups. And so if there were truly no difference between groups, the t-value would be 0 most of the time. And so this is like again, a sampling distribution if the null hypothesis was true. So we can see that most of the time, like there's a sort of a 0 t-statistic, or the t-statistic is like close to 0. As we sort of we get t-statistics that are bigger than 2, or like bigger than -2 also. This is where it's very unlikely that we would get a t-statistic that's this sort of extreme, meaning that there are really big group differences, if there was truly no difference in the population in terms of those groups. So the more extreme the t-value is, the more likelihood that the results are significant. And so as I mentioned earlier, sort of we have to choose a significance level. In this case, it's 0.05. And in this case, what you see is a two-tailed test where we have, this would be the case where if you didn't know, like if the t-statistic was going to be positive or negative, and so you have to sort of divide up that 5% significance level on either side of 0, you get a distribution that looks like this, where basically like if we have the chances that we would get a t-statistic that's like greater than -2.1 or positive 2.1 is 0.025%. And so if we essentially we add those two together, we get back our 0.05 significance level. So this is what's called a two-tailed test, because there's two sides of 0, essentially, where we're accepting significant results. This is what's called a one-tailed test. And here, this would be a case where like you predict that like there's going to be the t-statistic is going to be in one direction. Like we know it's going to be a positive value if the experiment worked. And so if you know it's going to be positive, you can sort of be more certain anyway that like, even if the t-statistic is a little bit less, we're still sure that that's different from 0. So a one-tailed test typically sort of has greater power than a two-tailed test because the t-statistic can be sort of a little bit closer to 0 and we would still be able to reject the null hypothesis. So again, I know it's sort of a lot of terms and it's a little confusing, but basically the main thing is that here we would reject the null hypothesis, which again sort of means that like the research hypothesis is supported. So rejecting the null hypothesis means that like we're rejecting the idea that there were no differences between groups. So that would imply that there are differences between groups. And we would do that if we have a t-statistic that's, in the case of a two-tailed test, either this extreme on either side of 0, or in a one-tailed test, it can be a little bit less extreme, but it needs to be on the sort of positive side. Another important term to just know what it is a confidence interval, which is also sort of related to the significance level. It's just sort of a different way of representing how confident you are that a study's findings are true or real in the population. So a confidence interval is essentially, it's a range of values that should capture the population value with a certain degree of confidence. And we often report 95% confidence intervals, which means that we're 95% confidence that like the population value of a particular statistic is going to be within this interval. So when you sort of see graphs, especially sort of like bar graphs that represent mean differences between groups, you often sort of see the confidence interval represented in this sort of a way where it's called an error bar because it's saying sort of like, this is the mean that we found in the sample, but because like we only had 10 people in it, we can't be like 100% sure that this is sort of the true mean value in the population. And so we have to sort of accept that within the population, if we want to be sort of 95% sure that it's going to be close to this mean difference, like this would be the interval that would capture that. And this would be the interval down here in the no model group. If we had a bigger sample size than just 10 people, those error bars would be smaller, which would mean that we have more confidence that like our mean from the sample is within a narrower range of possible values. So, so that's where like the sample size comes in, and that like the bigger sample you have, the more confidence you have, which actually results in a narrower confidence interval, meaning that we can be more sure that our sample findings are sort of reflecting the population. So I should have clicked this already, but basically, these were just the sort of mean scores that you saw previously in a graph form. And here again, you see the confidence intervals around them. So with statistical significance testing, it's all sort of based on probabilities rather than certainties. And so we have to sort of accept that, like, if we're, for example, if we have a 95% confidence interval, that means that like 19 out of 20 times, which would be 95%, we're going to sort of, that's going to capture the value that we have. But 5% of the time, we're going to be sort of wrong, in that there would be sort of a different value that's not within that confidence interval. So basically, yeah, there are errors that can happen when we use inferential statistics, and it's really just sort of a game of sort of what sort of errors can you accept and what sort of do you most want to avoid. And that would vary in different contexts, which we'll talk about. But ultimately, it's sort of helpful to think about this in terms of like a decision matrix, where you have two possible decisions you can make. You can either reject the null hypothesis, or you can fail to reject the null hypothesis. And there are two possible truths in which sort of you were either right or wrong to make that decision. So the possible decisions, again, are we reject the null hypothesis, which would mean that we sort of, the research hypothesis was supported. So rejecting the null hypothesis again, or rejecting the idea that there are no differences between groups. Or we can accept the null hypothesis, which would sort of say that like, oh, there actually are no differences between groups. The study didn't work. So those are the two decisions we can make. And then again, we're making these decisions based on probabilities, not certainties. And so the truth can be different from what we say. So either the null hypothesis was true, or the null hypothesis was false in the real world. And this will be, I think, become clear on this next slide here, where we're going to look at these sort of two possible decisions and two possible truths in terms of like a 2x2 decision matrix. So here we have the sort of columns within this matrix here is the true state in the population. So that's like, in reality, what are things actually like, which oftentimes we don't really know truly in reality what happens. Sometimes we may learn later that we made the sort of wrong decision, but for the sake of this example, let's say that, yeah, that we do have some way of knowing what's the true state in the population. So this would be the true state in the population. The null hypothesis is true, meaning that in reality in the population, there are no differences between groups. So that would capture these two, kind of this column. Or in the population, truly the null hypothesis could be false, meaning that like there are differences between groups. And then we have to sort of make a decision. So this is the like decision which we make based on sample data. And again, with inferential statistics, we're trying to decide if the sample data is reflective of the population. So we can either reject the null hypothesis, which are these two cases, or we accept the null hypothesis, which would mean like we're accepting the fact that there are no differences. And so within this 2x2 matrix, there's two correct decisions and two errors that we can make. So here are the correct decisions here, where if truly in the population, the null hypothesis is false, meaning that like the null hypothesis is saying that there are no differences, and that's false, meaning that there are differences, then we should reject the null hypothesis. So that would be the correct decision over here. If the null hypothesis was true, then we should accept the null hypothesis. So this would also be a correct decision. So that's what we sort of want to optimize the likelihood that we're going to make one of these correct decisions. However, yeah, so again, we're not always going to make the right decision, but we sort of have to accept some amount of error. And so we kind of separate that error into two main types, depending on like whether or not the sort of error that you're making. So that's either type 1 error or type 2 error. So type 1 error is basically saying that truly in the population, we should, like, there are no differences between groups. Like the intervention doesn't actually work. But we got some sample data that looked really nice, and it sort of implied that the experiment did work. So we rejected the null hypothesis, but that was a mistake. So we call that type 1 error. So it's like a sort of a false positive, and that we thought that what we found was real. In reality, it was a null finding. That's type 1 error. Think about it like a false positive. Type 2 error is more like a false negative, and that in the population, so the null hypothesis is actually false, and that like the experiment did work. There are differences between groups, but say maybe we didn't have a big enough sample size to detect that difference, or for whatever reason, like the data that we got due to sort of random error looked like there was no differences. So we accepted the null hypothesis. So that would be type 2 error. So just to define these in terms of words. So a type 1 error is made when we reject the null hypothesis, but the null hypothesis was actually true. So this is, again, sort of like a false positive. I'll just keep repeating this because rejecting the null hypothesis is sort of what you want to do as a researcher, because that you're rejecting the null hypothesis. That means that like the research hypothesis was supported. So going back to the example of the aggression experiment, that would mean that like we incorrectly conclude that the children exposed to aggressive models are more aggressive, when in reality, those two groups didn't actually differ in the population. And the probability of making sort of this sort of error in judgment, a type 1 error, this is where the significance or alpha level comes in. So the higher the significance or alpha level, the greater the probability of making a type 1 error. So we have to sort of decide this at the beginning of the study. What sort of probability are we willing to accept, or what amount of uncertainty are we willing to accept such that like we might make a mistake? And typically we sort of set that at 5%, like we're willing to set it to accept like a 5% risk that we make a mistake. And again, that's where the alpha level comes in. A type 2 error. So this is the sort of false negative. So this would occur when the null hypothesis is accepted. So as researchers, we get data that looks like, oh, the experiment didn't really work, darn. But in reality, it actually, like in the population, it actually would have worked. So the research hypothesis was actually true. So that would be the case that like we incorrectly conclude that children exposed to the aggressive models are not actually more aggressive. So again, like we incorrectly conclude that the experiment didn't work, but in reality, for this example, the two groups were actually different, and they would have actually differed in the population. So we can make this sort of error. It also has to do with the significance level that we choose. If we choose like too high of a significance level, like we have to say we want to be 99% sure, then sometimes that's going to make it harder to be able to reject the null hypothesis. So you'd be more likely to make a type 2 error instead. It also has to do with the sample size and effect size, such that with a really small sample size, the statistics are going to sort of always sort of be biased to say that like there are no differences between groups, because you just don't have enough people to reliably tell. And then same thing with an effect size, which we defined last week, but the effect size is just like how different were the two groups. So, or in the case of like a correlation, like how strong is the correlation? So it's just, the effect size is just like a standardized indicator of how big the findings were. And if the findings are really big, then we're going to be less likely to sort of make a type 2 error. Whereas if there's only sort of small differences and we have a small sample size, then we'll be pretty likely to make this sort of error in judgment. So to talk about this in a different context, like these sort of 2x2 decision matrix can really apply to any sort of decision-making context. And it just sort of depends on like what's the consequences of making these sort of wrong decisions in terms of which error do we most want to avoid, either a type 1 error or a type 2 error. So think about it. If you're a juror, your job is to sort of make some decision about whether or not someone committed a crime. And so the true state of things, which again, you don't really have access to as a juror, and you have to sort of, maybe you find out later or something, but sort of this is how things truly are in the population, but we don't have access to it. And truly in the population, either the person is innocent, which would, in this case, kind of like the null hypothesis is true, they didn't do a crime, or they're guilty and that the null hypothesis is false, so that they actually did do, there is a difference, or they did commit a crime. And we want to be sort of making these decisions where we find them guilty if they are guilty, or we find them innocent if they are innocent. However, there's again, these errors can come in, and with the way our sort of legal system is designed is like we sort of especially want to avoid type 1 errors, which would be a person is innocent, but we find them guilty. So that's like a false positive. And we want to avoid that just because like kind of that tends to be worse than a type 2 error. So this is why it's like you're innocent until proven guilty. And that it's, I guess this is sort of debatable from an ethical standpoint, and it would depend on like the exact circumstance, but typically like it is worse to put someone in jail for the rest of their life who is truly innocent, probably most of the time anyway, than sort of missing a few people when there actually is someone guilty, but we find them innocent. So the legal system anyway is set up such that like we're really trying to avoid these errors, and that sometimes means that we'll accept a little bit more of these errors. Obviously we want to avoid both, but that's the context for sort of our legal system. If you think about it like you're a doctor, it might be sort of a different trade-off in terms of making these sort of wrong decisions. Really, yeah, again, doctors want to be making the right decisions all the time anyway, but it can be worse to sort of make, in this case, what would be like a type 2 error, where the decision that a doctor makes is I'm not going to operate, and that like there's nothing wrong with you. I'm accepting the sort of null hypothesis, when in reality the null is false. Like there is something wrong with you and you do need an operation. So that would be sort of like something's going to get much worse, and this sort of type 2 error we want to avoid. And you also certainly want to avoid like doing unnecessary surgeries. So that would be saying, oh, there's something wrong with you, you need this sort of surgery, when in reality there wasn't. But debatably, and again, this would depend on the specific context, it's probably more often worse to sort of miss something. So with that, I know we've covered kind of a lot of stuff and a lot of content. That was sort of the majority of content we have for this week. So let's take a quick break, and then we'll sort of see what we can sort of finish when we come back. So we'll take 5 and come back at 10:55. All right, so sorry, I lost track of time a little bit there. So like I mentioned, we did cover that first half of class was the majority of the hard stuff from this chapter. So it's smoother sailing from here. And like I also said, like it's the sort of details behind everything that we talked about is covered in like at least a semester of a stats class if you were to go on to grad school, or it also will be covered like if you take intro to stats at the undergrad level in more detail, some of the stuff anyway. So really just the important thing is to understand the basics and to sort of get familiar with the sort of terminology, such like rejecting the null hypothesis. What does that mean? Because it's not super intuitive what it means, but again, I'll just keep repeating it so that it becomes more and more intuitive. But rejecting the null hypothesis is like you're saying that no, like I'm rejecting the idea that there's no differences between groups. So that would mean that we're supporting the research hypothesis and that there are differences between groups. So when we choose a significance level, which I've sort of talked about, that researchers sort of often choose an alpha or significance level of 0.05. They may also choose a 0.01 significance level too. It sort of just depends on how much like sort of how much risk they're willing to take in terms of making a type 1 error. So in general, sort of the alpha level that you choose or the significance level is going to specify the probability that you like your willingness to make a type 1 error. So this is sort of the same graph I showed earlier in terms of this would be like the sampling distribution of a t-test value if the null hypothesis was true. So in general, if the null hypothesis is true, like most of the time, 95% of the time anyway, we're going to get a value like somewhere around here. Whereas in 5% of the time, especially if we think that it's going to be like a positive t-value, there might actually, we'll get a value like up here, like a t-value that's up here, but it could actually still be a null finding. But again, we're willing to accept that risk because that's the specific alpha level that we chose of 0.05. So just to really illustrate, yeah, this text here sort of says what I just said, but with a 0.05 significance level, so an alpha level, again, of 0.05, there's a 5% chance that the population means are not actually different, even if we find differences in the sample. So we're accepting sort of a 5% chance of making a type 1 error. So here's just a question just to see if this is making some amount of sense. But say we have instead of 0.05 for an alpha level or significance level, I choose 0.01. So what would that imply in terms of what chance would I have of making a type 1 error with a 0.01 significance level? Yes, Ashley, you got it right. And so, yep, Chanel, you got it right too. So yeah, basically, I mean, if you think about it, just kind of what we saw up here, 0.05 significance level means that have a 5% chance of making a type 1 error. So if we choose a sort of more strict significance level of 0.01, we're going to have less of a chance of making a type 1 error. That also means that we actually are going to we'll have less of a chance of making this sort of false positive decision, but we'll have a higher chance of making like a false negative decision, that we're sort of raising the standards for what we need to find statistical significance. So that means that like we'll be more likely to say something is not significant when in reality there were population differences. So that's where it sort of gets tricky, and that you want to sort of choose a level that makes sense. And again, sort of where you're considering like what are the consequences of making a type 1 versus type 2 error. The And this would be sort of like when you, so this is the case if you're making a decision that like, oh, the findings are non-significant. So this is a type 2 error, basically, that the findings, the results of a study are non-significant, even though a relationship between the variables does exist in the real world. And so one of the main reasons in which this sort of type 2 error would happen is that you just didn't have a big enough sample size. Maybe you had difficulty recruiting participants for the study, and so you weren't able to get as many as you wanted. It could also be related to like, you don't get a very representative sample. And so that would be another reason why a type 2 error is happening. And then just like you have a funky representation of the population. So to see sort of what sample size would we need to detect a significant result with a specific alpha level, that's where you would do what's called a power analysis. And I think this power analysis is probably the last sort of complicated thing that we'll talk about today. But the power analysis is basically like you would use it to see what sample size do I need to detect an effect. So we say a power analysis, the power part of that term means like, so the power of a statistical test reflects the probability of correctly rejecting the null hypothesis with a specific sample size. So that means like the power is basically like, it's the probability of making the right decision. So correctly rejecting the null hypothesis. So you're making the right decision that the research hypothesis was supported and that we're rejecting the idea that there were no differences, which is again the null hypothesis, at a particular sample size. So the power is related to the sample size. And so generally speaking, sort of, it's related to also the effect size as well, which as I sort of talked about last week and earlier today, the effect size is just like, how different are the two groups if you're doing an experiment, or how strong is the correlation if you're doing a correlational study. So in general, if we want to have more power, we need more sample size. That's sort of a rule of thumb. If we have also sort of a smaller effect size, like we think we're going to have a weaker correlation or a smaller mean difference between groups, that means we need a larger sample size in order to have higher power or to find significant results for that small effect size. And in general, sort of what researchers aim for is like a power of about somewhere between like 0.7 and 0.9, 0.8 is the middle of those. And that's typically like what you want to have, at least 0.8 power to do a study. So if you have power of 0.8, that means like you essentially have like an 80% chance of correctly rejecting the null hypothesis with a specific sample. And again, that's also going to depend on the effect size. So this table sort of illustrates sort of what I'm talking about here, where again, sort of the power of a test is related to the effect size and the sample size. And so if we set power at a particular number that we want, so this is like 0.8 power, which is again what most researchers are aiming for. They want to have at least like an 80% chance of making the correct decision to reject the null hypothesis. So if we have a relatively small effect size, so a correlation of like 0.1, which is a pretty weak correlation. In order for that correlation to be significant, we have to have a sample size of 789 people. So that's kind of a lot of people, and it can be difficult to get that many people to take a survey or whatever. If we have a bigger effect size, we only need 200 people. So a 0.2 correlation, that's going to be statistically significant with only 200 people. And it's just going to keep going in this trend where like the bigger the effect size, the fewer number of people we need to have in the study to be able to say with 95% confidence that that correlation or that effect size is statistically different from 0. This is where like a lot of sort of planning comes into play, where if you're planning a study and say you want to predict something that is like just a complicated, like an outcome variable that's related to a bunch of other things, like actually like suicide is a good example in that like there are certainly like risk factors for suicide, and that like certainly depression is one of them, having high anxiety levels. There's other things too, but suicide is a very difficult outcome to predict. So any sort of variable that's correlated with suicide is going to have a really sort of small correlation in general. There's also just like a relatively low base rate of suicide. So if you want to do a study about like what predicts suicide, and you know that the correlations are going to be small between any particular variable and your outcome, that means you have to just have a ton of people in your study. So you probably need more than this, because you probably wouldn't even find a correlation of like 0.1 of any particular predictor with suicide. So again, like this is all sort of planning that you do before you do a study, when you think about how big of an effect size am I likely to have, and at a certain, if I want to have 80% power, that means that I need to have this many people participate in the study. So just kind of for the rest of this chapter is I think things that are generally speaking easier to understand, but still important, just about the sort of research process. So this was the second writing assignment where we talked about the importance of replications, where there was sort of this replication crisis that happened in psychology, like it's kind of almost like 10 years ago now, where basically they ran a bunch of replication studies, which is just redoing a study with like different participants. So you're resampling and having other researchers sort of do the study. They found that only 36% of studies replicated, and that sort of triggered this sort of broad movement towards research practices that promote replication. Because ultimately, like if we just find some results are significant in a single study, that means, again, with the sort of alpha levels that are common, like a 0.05 alpha level means that like 5% of the time we're going to sort of make a type 1 decision error. So 5% is too much to sort of definitively say anything from one study. So that's where we need to have like multiple studies that all find that same effect. And then if we have multiple studies that are all have like some only a 5% chance of making a mistake, the chance that all of those would show a significant result, when in reality, like there's not a significant result, is very, very small. So replication is super important for like the advancement of science and showing what sort of effects are truly real in the real world versus sort of what might, so sort of random error that you might find in a single study. In terms of like data analysis and software, so when you're running these statistical tests, this is again where like you would, I think in intro to stats, like the class that you take here at UH for undergrads, like you probably won't go into much use of these statistical programs, but maybe at least Excel. So it would depend on your instructor. But so you do statistical analyses in psychology, at least these are the main sort of programs that we use, especially R is becoming like sort of the most common in that it's free. These are other programs that are like companies own them, and so you have to pay for access to them, and it could be like renewing a license every year that can get fairly expensive. And so R, the statistical software, is if you're going to have to learn like one program to know that's be most useful if you're interested in like grad school in psychology, I would say that would be R. But also like if you know Excel pretty well, then that's great too, because you can do a ton of stuff in Excel and it's just fairly intuitive as well. When running an analysis, there's really sort of three main steps that you would do. And each of these steps is actually like many steps sort of combined. But the first step is inputting the data, and typically sort of data sets are set up such that like each row in you think about it like an Excel file is a participant, and then the columns are like different measures that that participant completed in the study. So just to be able to input data into a statistical software can be sort of complicated and requires a lot of data cleaning beforehand, where you have to sort of create all these scores for these different measures. You have to deal with missing data. That's, again, like sort of many steps all in one. But once you input the data, you would essentially type out, like, depending on what software you're using, different sort of like using programming language, or some software is like sort of point and click, like there's a drop down menu and you tell the software what to do. So maybe you say, I want to run a t-test to compare these two groups. And then the software is going to give you some sort of output that says, oh, the t-value is this. And you decide based on that t-value, is it big enough that you can make your sort of decision to reject the null hypothesis or not? So choosing different statistical tests, this is the last thing we have to cover today. Basically, like the sort of main thing that influences the right statistical test to run for any particular analysis is the types of variables that we have. And this is why we kept talking about these sort of 4 different types of variables that we have, which we also reviewed again last week. So depending on what variables we have, that will determine what analyses we should use. There's lots of sort of information you can find online about this. So you could just sort of Google, like, I have an ordinal variable and a nominal variable, and I want to see if there are differences in the ordinal variable across the nominal groups or something like that. Google will tell you something. And then also this sort of table is helpful. We kind of, I guess we have time to go through it, but remember nominal groups. So this is where all of this is sort of like, if we have 2 variables, and we have an independent variable over here, and then this is the dependent or the outcome variable. So if we had, these are all cases with a nominal. So this is like a categorical predictor variable or independent variable. So if you wanted to compare basically whether or not, like, there are statistical differences between right-handed and left-handed people. So that's the predictor, your handedness, and whether or not you're a vegetarian, which is also a nominal variable because it's either a yes or no. You would use a chi-square test. If you wanted to see if there are differences between right-handed and left-handed people in their grade point average is an interval or ratio scale. Then you would use a t-test. So then again, this is where we talked about earlier, like you're comparing mean differences. So mean differences in terms of GPA across right-handed and left-handed people. If you had 3 or more groups, so now instead of like handedness, you have how much time did someone study, and we're just going to group people. They spent low time, medium time, a lot of time. And the outcome is the test score. It's also an interval ratio scale. Then we would use what's called an ANOVA, or a one-way analysis of variance. This is what we've talked about a lot in previous weeks. If we have 2 sort of continuous variables, or 2 variables that are measured on an interval or ratio scale, like how optimistic you are and how many days you were sick last year, that's where we use correlations, where we can have like a nice scatter plot to see how those 2 continuous or numeric variables are related to each other. And then finally, just the last 2 here. So if we have more than 2 categories, so if we have a nominal variable with as the predictor, and an outcome that's a numeric or interval ratio variable, then we would use, again, what's called an analysis of variance, but a factorial design. And then finally, if you have more than 2 or more like sort of predictors and 1 outcome that's also an interval ratio scale, that's where multiple regression would come in. We talked about this last week a little bit. I think overall, you don't need to know a ton from that table, but you should know like the basics of these different tests, and especially the ones that we've covered in class. So that would be correlations, especially, and then what we just covered today, which was t-tests. So when would you run a correlation versus when would you run a t-test? Here's the poll for the week. They take 2 minutes to do it, and then I'll go through the answers real quick. All right, take 20 more seconds. Just make a guess if you haven't yet. So I'll go through the answers. Keep making a guess. At this point, if you don't know, just make sure you click submit. Still waiting on 5 people, 4 people. You have 5 more seconds. Okay. So I just wanted to sort of test understanding about some of the things I really tried to drive home today. It looks like most people got the first 2 right. So in an experiment with 2 groups, the null hypothesis, again, null means like no findings. So that would mean that the 2 groups do not differ from one another. In a correlational study, the null hypothesis would predict that the correlation between the 2 variables is not statistically different from 0. So it's null. It's a correlation that we can't say is greater than 0. If a researcher concluded that the experimental manipulation had an effect, but in reality it did not, this would be a type 1 error. So that would be like, again, a false positive where we're saying that we're rejecting the null, meaning that we're saying that the experiment did have an effect, but in reality there was no difference. That's the false positive type 1 error. And then finally, a t-test is used, yeah, most people got this one right, to test whether 2 groups, so you need to have like a nominal variable, are different from each other on typically like an ordinal variable. So you can have like an interval ratio variable, sorry. So you can have like a mean. So you have a mean score for these 2 groups and you're seeing whether or not that mean score is statistically different. So that's all for today. I just had 2 sort of review slides, which you can find in the slides when I post them. Otherwise, yeah, that's it. So have a good rest of your week. Email me if you have any questions. Otherwise, I'll see you next week.
Thank you. Have a good week.